Okay, ionic bonding. So ionic compounds consist of ions held together in a lattice structure by ionic bonds, and you can see they're a representation of a lattice. This is what we need to know by the end of it. Positive ions, cations, formed by metals losing their outer electrons, their valence electrons. So that word cation is because they're attracted to a cathode, which is your negatively charged electrode in a cell. Negative ions or anions formed by nonmetals gaining electrons. Number of electrons lost or gained is determined by the electron configuration of an atom, so we're really just working with the valence electrons. The ionic bond is due to electrostatic attraction between oppositely charged ions, and under normal conditions ionic compounds are solid with lattice structures. Right, so if we think of some of these substances and in terms of their electron configurations and what's in their outer shell, probably is a very quick way we can just think, well, what group are they in? Well, this is in group 1, lithium. Its actual electron configuration is 2,1. It's going to lose, it's a metal, it's going to form a cation, it's going to lose its outer electron, it's going to become Li+. Magnesium, group 2, it's going to lose its 2 outer electrons, it's going to become Mg2+. Now you have to be a little careful with our transition metal elements because they can often form a variety of ions. When we talk more about the D block you'll understand why. But iron potentially could be these and some others as well it has open to it. Those are probably the two most common forms. The non-metals, they're going to form anions. Oxygen's in group 6, so it's got 6 outer electrons. There it is. Rather than losing all 6, it's going to pick up 2 electrons, so that's going to become O2-. Fluorine, group 7, it's going to pick up 1 to finish the outer shell, it's going to become F-. Right, so we've also covered these in an earlier section, polyatomic ions or compound ions, and these can obviously also form ionic compounds because we've got electrostatic interactions possible. Just be careful, within here we've got covalent bonding, but then when they form an actual compound like this, then that's where we've got our ionic bond. So between the metal and this group, that's our ionic interaction, but within here that's a covalent bond, which we'll see more in the next section. So ionic bonding, we're looking at, it's the metals are giving up their electrons, the non-metals are gaining them, and we're ending up with this attraction between the two. So we've got positives, we've got negatives, and if we're thinking about the formulae, well, if we've got something that's ending up 2-, we're going to need 2 positives with it if we're going to form a neutral lattice. So when do we see ionic bonds being formed between elements? It's when there's a large difference in electronegativity. Right? If the electronegativities are close, and again we'll talk more about this in the next unit, if they're close, then we're going to describe it as covalent. They're going to share the electrons. But if they're very different, then we get complete transfer of electrons. And so in aluminium oxide, the aluminium loses its electrons, oxygen's picking up electrons, and we get an ionic electrostatic attraction. Whereas something like aluminium bromide, where there's less of a difference in electronegativity, then that can be regarded as a covalent compound where they're actually sharing electrons rather than complete transfer. So we learned earlier on how to write formulae using our combining powers. Now the idea behind the combining powers essentially came down to this idea of ions largely. So if you think of something like fluorine, we said, oh, that's in that 7th group, its combining power is 1. You can see the charge on a fluoride ion is -1. And so what we're doing is just combining these to end up with a lattice that doesn't have a charge. So if we want potassium fluoride, it's going to be 1K and 1F, K plus F minus. If we wanted calcium fluoride, we would need 2 of the F minuses to balance up with that 2 plus there. If we wanted aluminium fluoride, it would be AlF3. So likewise, we maybe need to go things a bit more complicated, scale things up if we're doing, let's say, aluminium sulfate. Aluminium sulfate, there we go. So this is 3 plus, this is 2 minus. So what we're going to need is 2 of the aluminiums to give us a 6 plus, for our sulfate to also get 6 minus, we're going to need 3 of those, like that. So it's maybe worth your while taking a bit of time just to practice some combinations from these cations and the anions, and write some new formulae. Right, this lattice that's produced, whilst we're talking on this earlier slide about, well, LIF, it's not just a pair of these ions, right? It is a regular repeating pattern of lithium surrounded by fluorides and fluorides surrounded by lithiums, and it goes on. It's this big three-dimensional array, which we're going to call a lattice. As such, if you were to try and break that down, you'd have to break down all of these electrostatic interactions, and it means that they have very high melting points. They don't form vapors very easily. It's not going to conduct electricity, because for something to conduct, we need free moving charged particles. And at the moment, all of these charges, the Li pluses and the F minuses, they're locked in position. It's only when you melt it or you dissolve it, if it dissolves, that they'll be free to move around and it can conduct electricity. So in terms of whether something dissolves, some ionic substances are soluble, some aren't. Something like magnesium oxide isn't, but something like sodium chloride is. There's 2 factors at work. There's how strong the lattice is, how much energy it takes to break that down, and then there's how much energy you get back when these ions are in the water and they're able to be solvated by water molecules. So there's these interactions with waters, electrostatic attraction there, and whether we have that or not, how much of it, whether there's enough to offset the lattice energy. So probably more on that in the energetic section. But as a rule, lattices, high melting point, low volatility, sometimes soluble, they conduct once you've broken down that lattice, when they're molten or in solution. Right, this is what we've been through, that's what we've covered.